Hello, and good morning, good night, or whatever the case may be. We'll be continuing off from yesterday's Let's Study series episode with another Let's Study episode on Intro to 3D Game Programming with DirectX12. Last recording, we left off with recreating or rebuilding the box demo from the book's source code, which we sourced from the book's website. And now we'll be continuing on into the mathematical prerequisites before the rest of the book. So we just put this aside. Okay, and then we have part 1 on mathematical prerequisites. And we have a quote from Roger Bacon. For the things of this world cannot be made known without a knowledge of mathematics. The things of the world cannot be made known. Yes. We need mathematics in order to know things. The tools it applies is, quite important. Video games attempt to simulate a virtual world. However, computers, by their very nature, crunch numbers. Thus, the problem of how to convey a world to a computer arises. The answer is to describe our worlds and the interactions therein completely mathematically. Consequently, mathematics plays a fundamental role in video game development. In this prerequisites part, we introduce the mathematical tools that will be used throughout this book. The emphasis is on vectors, coordinate systems, matrices, and transformations, as these tools are used in just about every sample program of this book. In addition to the mathematical explanations, a survey and demonstration of the relevant classes and functions from the DirectX Math library are provided. Note that the topics covered here are only those essential to understanding the rest of the book. It is by no means a comprehensive treatment of video game mathematics, as entire books are devoted to this topic. For readers desiring a more complete reference to video game mathematics, we recommend Verfo 4 and Langley 02. Those must be bibliography indexes. Okay. Chapter 1. Vector Algebra. Vectors are, perhaps, the most fundamental mathematical objects used in computer games. We use vectors to represent positions, displacements, directions, velocities, and forces, for example. In this chapter, we study vectors and the operations used to manipulate them. Chapter 2 covers matrix algebra. Matrices provide an efficient and compact way of representing transformations. In this chapter, we become familiar with matrices and operations defined on them. Chapter 3, Transformations. This chapter examines 3 fundamental geometric transformations: scaling, rotation, and translation. As we use these transformations to manipulate 3D objects in space. In addition, we explain change of coordinate transformations, which are used to transform coordinates representing geometry from one coordinate system into another. Chapter 1 on Vector Algebra. Vectors play a crucial role in computer graphics, collision detection, and physical simulation, all of which are common components in modern video games. Our approach here is informal and practical. For a book dedicated to 3D games and graphics math, we recommend Verfo 4. We emphasize the importance of vectors by noting that they are used in just about every demo program in this book. Objectives for Chapter 1 on Vector Algebra. to learn how vectors are represented geometrically and numerically, to discover the operations defined on vectors and their geometric applications, and to become familiar with the vector functions and classes of the DirectX math library. Section 1. Vectors. A vector refers to a quantity that possesses both magnitude and direction. Quantities that possess both magnitude and direction are called vector-valued quantities. Examples of vector-valued quantities are forces. A force is applied in a particular direction with a certain strength or magnitude. Displacements, the net direction and distance a particle moved, and velocities, both speed and direction. Thus, vectors are used to represent forces, displacements, and velocities. In addition, we also use vectors to specify pure directions, such as the direction the player is looking in a 3D game, the direction a polygon is facing, the direction in which a ray of light travels, or the direction in which a ray of light reflects off a surface. A first step in categorizing a vector mathematically is geometrically. We graphically specify a vector by a directed line segment. See Figure 1.1. Where the length denotes the magnitude of the vector and the aim denotes the direction of the vector. We note that the location in which we draw a vector is immaterial because changing the location does not change the magnitude or direction, the two properties a vector possesses. Therefore, we say two vectors are equal if and only if they have the same length and they point in the same direction. Thus, the vectors u and v, drawn in Figure 1.1a, are actually equal because they have the same length and point in the same direction. So we have these vectors here, u and v. They have the same length and they point in the same direction. They're parallel. The only difference is where they are drawn. Where they are drawn. In fact, because location is unimportant for vectors, we can always translate a vector without changing its meaning, since a translation changes neither length nor direction. Observe that we can translate u such that it completely overlaps with v, and conversely, thereby making them indistinguishable, hence their equality. As a physical example, the vectors u and v in Figure 1.1b both tell the ants at two different points, A and B, to move north 10 meters from where they are. Again, we have that u equals v. The vectors themselves are independent of position. They simply instruct the ants how to move from where they are. In this example, they tell the ants to move north, direction, and 10 meters length. V and U, point A, point B, we have a coordinate system key, up is north, U and V point up north. Section 1.1, Vectors and Coordinate Systems. We could now define useful geometric operations on vectors, which can then be used to solve problems involving vector-valued quantities. However, since the computer cannot work with vectors geometrically, we need to find a way of specifying vectors numerically instead. So what we do is introduce a 3D coordinate system in space and translate all the vectors so that their tails coincide with the origin. Figure 1.2. Then we can identify a vector by specifying the coordinates of its head and write v equals x, y, z, as shown in figure 1.3. Now we can represent a vector with 3 floats in a computer program. And we have a note here. If working in 2D, then we just use a 2D coordinate system, and the vector has 2 coordinates, an x and a y, and we can represent a vector with 2 floats in a computer. Consider figure 1.4. which shows a vector v and 2 frames in space. Note that we use the terms frame, frame of reference, space, and coordinate system to all mean the same thing in this book. We can translate v so that it is in standard position in either of the 2 frames. Observe, however, that the coordinates of the vector v relative to frame A are different from the vector coordinates of the vector v relative to frame B. In other words, the same vector v has a different coordinate representation for distinct frames. The idea is analogous to, say, temperature. Water boils at 100 degrees Celsius, or 212 degrees Fahrenheit. The physical temperature of boiling water is the same no matter the scale. For example, we can't lower the boiling point by picking a different scale, but we assign a different scalar number to the temperature based on the scale we use. Similarly, for a vector, its direction and magnitude, which are embedded in the directed line segment, does not change. Only the coordinates of it change, based on the frame of reference we use to describe it. This is important because it means whenever we identify a vector by coordinates, those coordinates are relative to some frame of reference. Often, in 3D computer graphics, we will utilize more than one frame of reference, and therefore we will need to keep track of which frame a vector's coordinates are relative to. Additionally, we will need to know how to convert vector coordinates from one frame to another. We have a note here. We see that both vectors and points can be described by coordinates x, y, z relative to a frame. However, they are not the same. A point represents a location in 3 space, whereas a vector represents a magnitude and direction. We will have more to say about points in Chapter 1, Section 5. Section 1.2. Left-handed versus right-handed coordinate systems. Direct3D uses a so-called left-handed coordinate system. If you take your left hand, aim your fingers down the positive x-axis, and then curl your fingers toward the positive y-axis. Your thumb points roughly in the direction of the positive z-axis. So I'm going to get my hands in doing this. Okay. I think I understand. Observe for the right-handed coordinate system. If you take your right hand and aim your fingers down, the positive... Oh, okay. Fingers, like the whole palm. Alright, so take your left hand and aim your fingers down the positive x-axis. Okay? And then curl your fingers towards the positive y-axis. Your thumb points roughly in the direction of the positive z-axis. Okay. That's a different way of doing it. Sort of like a palm, curl, thumb points in the direction. Okay? I usually do, like, it's almost like a gang sign. My pointer and middle finger, where I point down X with my middle finger at a 90-degree angle to the x-axis, pointing Y, and then my thumb points Z. So there's a different way of doing it. Observe that for the right-handed coordinate system, if you take your right hand and aim your fingers down the positive x-axis, and then curl your fingers towards the positive y-axis, your thumb points roughly in the direction of the positive z-axis. And we have figure 1.5 below showing this, without the hands. Section 1.3, Basic Vector Operations. We now define equality, addition, scalar multiplication, and subtraction on vectors using the coordinate representation. For these four definitions, let u equal u of x, u of y, and u of z, and v equals v of x, v of y, and v of z. Two vectors are equal if and only if their corresponding components are equal. That is, u is equal to v if and only if u of x equals v of x, u of y equals v of y, and u of z equals v of z. We add vectors components-wise. So the vectors u plus v equals the component-wise summations of x's, of y's, and of z's. So we have u plus v is equal to u of x plus v of x, u of y plus v of y, and u of z plus v of z. Observe that it only makes sense to add vectors of the same dimension. We can multiply a scalar, i.e. a real value, and a vector, and the result is a vector. Let k be a scalar. So then, k times u is equal to k times u sub x, k times u sub y, and k times u sub z. This is called scalar multiplication. We define subtraction in terms of vector addition and vector and scalar multiplication. That is, u minus v is equal to u plus negative 1 times v. So u is added to the scalar inverse of v. U sub x minus v sub x, u sub y minus v sub y, and u sub z minus v sub z. Example 1.1. Let u equal 1, 2, 3. V equal 1, 2, 3. W equal 3, 0, minus 2. and k equals 2. Then, problem 1, u plus w is equal to the vector u, 1, 2, 3, plus the vector w, 3, 0, minus 2. And so 1 plus 3 is equal to 4. 2 plus 0 is 2, and 3 plus minus 2 is 1. We say that u is equal to v, in which case u sub x is 1, v sub x is 1, u sub y is 2, v sub y is also 2. And finally, u sub z is 3, and v sub z is also 3. So u equals v is correct. Now we have u minus v, which is equal to u plus the minus of v, or the inverse of v. This is equal to the vector u, 1, 2, 3, plus the vector v, which is minus 1, minus 2, minus 3 now. And when we add these together, the 1 plus minus 1 is 0, 2 plus minus 2 is 0, and 3 minus 3 is 0. And so the vector is 0. Finally, we have example problem 4, k times w, where k is a scalar value of 2, and w is the vector 3, 0, and minus 2. And so if we distribute the scalar to all of the components of the vector w, we have 2 times 3, which is equal to 6. 2 times 0 is 0, and 2 times minus 2 is minus 4. The difference in the third bullet illustrates a special vector called the 0 vector, which has zeros for all of its components and is denoted by 0. Example 1.2. We will illustrate this example with 2D vectors to make the drawings simpler. The ideas are the same as in 3D. We just work with one less component in 2D. So it looks like the typesetting program failed to write this correctly. Or the scan did. It's hard to say. Effectively, I think in example 1, I'm trying to read between the lines, that minusing a vector is negating a vector can be thought as flipping its direction. And a scalar multiplication can be thought of scaling the length of a vector. So if we multiply a vector, if we minus a vector, we flip its direction. And if we multiply a vector by some scalar value, if it is a scalar value of 2, we'll double its length. If it's a scalar value of a half, or 1 over 2, then we'll half it in length. So we're scaling the length of the vector. Example problem 2 shows that vector addition means geometrically. We parallel translate u so that its tail coincides with the head of v. Then the sum, so u plus v, then the sum of the vector originating at the tail of v and ending at the head of the translated u. We get the same result if we keep u fixed and translate v so that its tail coincides with the head of u. So we're going to see this in the figure 1.6. So we can see here, we have the vector v, represented by 2 and 1. Scalar multiplication of -1 flips the direction, and then 1 over 2 divides its length in half. And then in figure 1.6b, this is we have the vector v with 1 and 2, and a vector u of 2 and 1/2. And if we translated the vector up along v such that its tail and its head, or its start and its finish, if its start finishes or lands or is placed on the finish of v, we can continue drawing u in its direction and its magnitude to reach a new location. And that location is the combination, the addition of u and v. Essentially, the difference v minus u gives us a vector aimed from the head of u to the head of v. If we instead interpret u and v as points, then v minus u gives us a vector aimed from the point u to the point endpoint v. This interpretation is important as we will often want the vector aimed from one point to another. Okay, so we have vector u down here, and the vector v, and then we have v minus u is shown here, and this v minus u is the same as the vector from the head of u to the head of v, and translated to the coordinate system origin. In figure 1.7, forces applied to a ball. The forces are combined using vector addition to get a net force. So we have a force F of 1 applying to the ball, and then we have the force F of 2 greater than F of 1 applying to the ball as well, and then the combined force F of 1 plus F of 2 is the final direction of acceleration. And we have the similar problem, with the major difference is that we're applying a negative force of F of 1, a minus of F of 1 force, and F of 2 remains the same. Section 2. Length and unit vectors. Geometrically, the magnitude of a vector is the length of the directed line segment. We denote the magnitude of a vector by double vertical bars. For example, double vertical bars surrounding u denotes the magnitude of u. Now, given a vector u, which has an x, y, and z component, we wish to compute its magnitude algebraically. The magnitude of a 3D vector can be computed by applying the Pythagorean theorem twice. See figure 1.8. First, we look at the triangle in the xz plane with sides x and z and the hypotenuse a. From the Pythagorean theorem, we know that a is equal to the square root of x squared plus z squared, and the hypotenuse is the magnitude of u. From the Pythagorean theorem again, we arrive the following magnitude formula. where the magnitude of u is the square root of y squared plus a squared. So it looks like we have the triangles here represented by the origin along the x-axis to this z value and to this x value length along the x-axis, and then the z-axis length, and you have a 90-degree angle in here. So a right here is equal to x squared plus z squared, and these are square rooted. The square root of x squared plus b squared, or the Pythagoras theorem is a squared equals x squared plus z squared. And so once we find a, we now have the length of a 90-degree angle up into the y, and from this we have our right angle triangle, and then the only remaining length we don't know is the length from tail to head, or the u vector. So when we find this value here, which we represent with the double vertical bars of u, a squared plus y squared under a square root, or the square root of a squared, the magnitude of u squared is equal to this a squared is a squared plus y squared. And so if we square root both sides, we end up that the magnitude of u is equal to the square root of a plus square root of a squared plus y squared. For some applications, we do not care about the length of a vector because we want to use the vector to represent a pure direction. For such direction-only vectors, we want the length of the vector to be exactly 1. When we make a vector unit length 1, we say that we are normalizing the vector. We can normalize a vector by dividing each of its components by its magnitude. So we have u with a little hat on top, and that is equal to the vector u divided by its magnitude. The 3D length of a vector can be computed by applying the Pythagorean theorem twice. To verify this formula is correct, we could compute the length of u sub hat. U sub hat is equal to the square root of x u sub hat, the magnitude of a unit vector, is the square root sum of x divided by the magnitude of u squared plus y divided by the magnitude of u squared plus z divided by the magnitude of u squared. If we then distribute the square into x and the magnitude of u, and x divided by u, y divided by u, z divided by u, we can have the square root of x squared over u squared plus y squared over u squared plus z squared over u squared. And then we can separate out, we can factor out the square root of u squared, or we can factor out the square root, we can factor out u squared out of all of the x squared, y squared, z squareds, separate them, and then we can apply the square roots separately, and then we know that the square root of a square is just the element. So u squared, square root of u squared is just u. And we know by Pythagoras definition, I'm not sure if this is a very good proof, but the square root of x squared plus y squared plus z squared is equal to u as well. And u divided by u is simply 1. So u sub hat is indeed a unit vector. I'm pretty sure you could prove it with here, down here. This is more of the proof. We just didn't have it over here. Example 1.3. Normalize the vector v is equal to minus 1, 3, and 4. We have the magnitude of v is equal to the square root of minus 1 squared plus v squared plus 4 squared, which is equal to the square root of 26. Thus, v sub hat is equal to v, or the vector v, divided by the magnitude of v, which we have found to be the square root of 26. So now v sub hat is equal to minus 1 over square root of 26, 3 over square root of 26, and 4 over the square root of 26. To verify that v sub hat is indeed a unit vector, we compute its length. So we have the magnitude of v sub hat is equal to the square root of its x component squared plus its y component squared plus its fourth component squared. It's z component squared. So if we square root minus 1 over the square, if we square minus 1 over the square root of 26, we'll get 1 over 26. If we square 3 over square root of 26, we get 9 over 26. And if we square 4 over square root of 26, we will get 16 over 26. If we add up 1 over 26 plus 9 over 26 plus 16 over 26, we will get 26 over 26, 1 over 1, or the square root of 1, which is equal to 1. And a vector length is defined as having a length of 1. A unit vector is described as having a unit length of 1. Section 3. The dot product. The dot product is a form of vector multiplication that results in a scalar value. For this reason, it is sometimes referred to as the scalar product. Let u is equal to u sub x, u sub y, and u sub z, and v is equal to v sub x, v sub y, and v sub z. Then the dot product is defined as follows, with u dot v is equal to u sub x times v sub x plus u sub y times v sub y plus u sub z plus v sub z. And in words, the dot product is the sum of the products of the corresponding components. The dot product definition does not present an obvious geometric meaning. Using the law of cosines, see example 10, we can find the relationship that u dot v is equal to the magnitudes of u and v times the cosine of the angle between them. With figure 1.9 showing, in the left figure, the angle theta between the vector u and v is an acute angle. In the right figure, b, the angle theta between u and v is an obtuse angle. When we refer to the angle between two vectors, we always mean the smallest angle. That is the angle such that theta is greater than or equal to 0 and less than or equal to pi. That's not right. That's not possible. You cannot be both equal to 0 and pi at the same time. That relation is wrong. Where theta is the angle between the vectors u and v, such that theta is greater than or equal to 0 and less than or equal to pi. See figure 1.9. So, equation 1.4 says that the dot product between two vectors is the cosine of the angle between them scaled by the vector's magnitudes. In particular, if u and v are unit vectors, then u times v is the cosine of the angle between them, i.e. u dot v equals cosine of theta. Equation 1.4 provides us with some useful geometric properties of the dot product. So, example 1. If u dot v is 0, then u is perpendicular to v, or the vectors are considered orthogonal to each other. If u dot v is greater than 0, then the angle theta between the two vectors is less than 90 degrees. The vectors make an acute angle. If u dot v is less than 0, then the angle between the two vectors is greater than 90 degrees, i.e. the vectors make an obtuse angle. The word orthogonal can be used as a synonym for perpendicular. And we have example 1.4. Let u equal 1, 2, and 3, and v equal to -4, 0, -1. Find the angle between u and v. First, we compute. U dot v is equal to 1, 2, 3 dot -4, 0, -1, which is equal to 1 times -4 to be -4 plus 2 times 0, which is 0, so we don't even write it. And we have 3 times -1, which is -3, so -4 plus -3 is equal to -4 minus 3, which is equal to -7. We have the magnitude of u equaling the square root of its x component squared, its y component squared, and its z component squared, which is 1 squared, 2 squared, 3 squared, which is 1, 4, 9. 1 plus 4 plus 9 is 14. So the magnitude of u vector is the square root of 14. And then to find the magnitude of vector v, we take the square root of the sum of its x component, y component, z component squared, respectively. With -4 squared, 16, 0 squared, 0, and -1 squared, which is 1. So we have 16 plus 1 under a square root, so the magnitude of vector v is equal to the square root of 17. Now, applying equation 1.4 and solving for theta, we get. So we have u dot v is equal to the magnitude of u times the magnitude of v times cosine of theta. But if we divide both sides by the magnitude of u and times the magnitude of u and v, we cancel out the magnitudes of u and v on the cosine of theta side and bring them over to the u dot v side. And so we have u dot v, which we calculated above, to be minus 7 divided by the summation, well, not summation, the product of the magnitudes of u and v, which is as calculated above. We substitute them in. We have the magnitude of u being square root of 14 and the magnitude of 17 as the magnitude of v as square root of 17. So we have minus 7 over minus 14 times minus 17. And then if we a cosine or inverse cosine both sides of the equation, we cancel out cosine on the theta side of the equation, and we have the inverse cosine of our right-hand side of the equation, which is minus 7 over the square root of 14 times the square root of 17. And if we punch that into a calculator, we will get about 117 degrees is the theta angle between u and v, the smallest angle between u and v. And we have example 1.5. Consider figure 1.10. Given v and a unit vector n, find a formula for p in terms of v and n using the dot product. First observe from the figure, let's check figure 1.10, here we are. So we have two coordinate systems drawn. They appear to be looking the same directions. We have an x and a y, so it's a 2D problem. We have the vector v shown in we have the vector v shown on the left-hand side going to the upper right. So its x and y component are positive, but on the right-hand side, the x component of v is now minus. We have a vector w, which is equal to v minus p, which p, the vector p, runs along the x-axis and has the same x-axis magnitude as v. And so w is equal to v minus p, which effectively removes the x component of v, such that w is now lying completely on the y-axis. Which is the same on the right side, the other coordinate system. And we have p shown on the right-hand side. On the right coordinate system, we have v and p, so we're not going to consider them the same v's. So they're different v's in different situations. Well, here's the thing. V does not equal v in this example. Why? Because they have a different direction. The x component is different. Since they don't have the same x direction, they cannot be the same vector in the same space. So it's v and v star on the right-hand side, I guess. And we have a vector p along the negative x-axis, or along the x-axis in the minus direction, up to point K from the origin. And if we subtract v by p, we get the vector w, which is only the vertical component of vector v, only the y component of vector v, since the x component of vector p and v cancel each other out, since they both have the same magnitude in the direction of x-axis. We have section 3.1, orthogonalization. A set of vectors v sub 0 to v sub n minus 1 is called orthogonal if the vectors are mutually orthogonal. Every vector is a set in the set is orthogonal to every other vector in the set and unit length. Mutually orthogonal and or also unit length. Sometimes we have a set of vectors that are almost orthogonal, but not quite. A common task is to orthogonalize the set and make it orthonormal. In 3D computer graphics, we might start off with an orthonormal set, but due to numerical precision issues, the set gradually becomes unorthonormal. We are mainly concerned with 2D and 3D cases of this problem, that is, sets that contain 2 and 3 vectors, respectively. We examine the simple 2D case first. Suppose we have a set of vectors v sub 0 and v sub 1 that we want to orthogonalize into an orthonormal set w of 0 and w of 1, as shown in figure 111. We start with w of 0 is equal to v sub 0 and modify v sub 1 to make it orthogonal to w of 0. This is done by subtracting out the portion of v sub 1 that acts in the w of 0 direction. So we have the w sub 0 direction, and v sub 1, and we are subtracting the projection of v sub 1 on w sub 0 to get w sub 1. We now have a mutually orthogonal set of vectors, v sub 0 and v sub 1. So we're setting w sub 0 to equal v sub 0 here. And then we're moving the lack of orthogonalization, the component here, to w sub 1. The last step to constructing the orthonormal set is to normalize w sub 0 and w sub 1 to make them unit length. The last step. That's quite easy. The 3D case follows in the same spirit as the 2D case, but with more steps. Suppose we have the set of vectors v sub 0, v sub 1, and v sub 2 that we want to orthogonalize into an orthonormal set of w sub 0, w sub 1, and w sub 2, as shown in figure 1.12. We start with w sub 0 is equal to v sub 0, as we did before, and modify v sub 1 to make it orthogonal to w sub 0. This is done by subtracting out the portion of v sub 1 that acts in the w sub 0 direction. So we have w sub 0 is equal to v sub 0, and then v sub 1 to w sub 1. So we make w sub 1 now orthogonal to w sub 0 by this method. And then we repeat this on w sub 2, of v sub 2 twice, where we do the projection of we get w of 2 based on the projection of v sub 2 on w of 0 here. And we also subtract the projection of v sub 2 on v sub 1 on the y-axis. And we move these x and y-axis components, we leave only the z-axis component. So we're canceling out components. So we have v sub 1, v sub 0, v sub 2. 0, 1, 2. Okay? And we have we set v sub 0 to be on the x-axis. We remove the x and y, well, in this case, only the x-axis and component of v sub 1. And then for v sub 2, we remove an x and a y component to get only. We cancel out the x and y component to leaving only the z component, w of 2. For the general case of n vectors, so v sub 0 to v sub n minus 1, we want to orthogonalize into an orthonormal set of w sub 0 to w sub n minus 1. We have the following procedure commonly called the Gram-Schmidt orthogonalization process. Where the base step is we set the first vector to be equal to the v sub 0, and then for every vector we want to set the next vector to equal the projection to equal the vector minus the projections of that vector on all other vectors starting from the vector it's onward. And then finally, we normalize all of the vectors of all of the vectors of w, the set of w sub I vectors by their magnitude. So we normalize each vector w sub. Again, the intuitive idea is that when we pick a vector v sub I from the input set and add to the orthonormal set, we need to subtract out the components of v sub I that act in the directions of the other vectors, v sub 0, v sub 1, v sub I minus 1, that are already in the orthonormal set to ensure the new vector being added is orthogonal to the other vectors already in the orthonormal set. And there is section 4, the cross product. The second form of multiplication vector math defines is, so the second form of multiplication vector math defined as the cross product, unlike the dot product. Unlike the dot product, which evaluates to a scalar, the cross product evaluates to another vector. Moreover, the cross product is only defined for 3D vectors. In particular, there is no 2D cross product. Taking the cross product of two 3D vectors u and v yields another vector, say w, which is mutually orthogonal to u and v. By that, we mean that w is orthogonal to u and w is orthogonal to v, both. Figure 1.13. See figure 1.13. So we have the vector u and the vector v, and then we have the vector w, which is the cross product of u and v. If u is equal to u sub x, u sub y, and u sub z, and v is equal to v sub x, v sub y, and v sub z, then the cross product is computed like so. W is equal to u cross v, which is equal to u sub y times u sub v minus u sub z times u sub y as the first component, the x component. We have u sub z times v sub x minus u sub x times v sub x as the y component. And then we finally have u sub x times v sub y minus u sub y times v sub x for our z component of this cross product vector w of u cross v. Note: if you are working in a right-handed coordinate system, then you use the right-hand thumb rule. If you take your right hand and aim your fingers in the direction of the first vector u, and then curl your fingers toward v along the closest angle to v, then your thumb roughly points in the direction of w, which is u cross v. With figure 1.13, the cross product of two 3D vectors u and v yields another vector w that is mutually orthogonal to u and v. If you take your left hand and aim your fingers in the direction of the first vector u, and then curl your fingers towards v along an angle closest between u and v, then your thumb roughly points in the direction of w, which is u cross v. This is called the left-hand thumb rule. Let example 1.6. Let u equal the vector 2, 1, 3, and v be the vector 2, 0, 0. Compute the cross product of u and v as w, and z being the cross of v cross u, and then verify that w is orthogonal to u and that w is orthogonal to v. Applying equation 1.5, we have w is equal to u cross v, which is equal to the vector u of 2, 1, 3 cross the vector v, which is 2, 0, 0. And I see what the author did here. They added a lot of zeros, so it would cancel out and be nice and easy. But we have 1 times 0 minus 3 times 0. We have 3 times 2 minus 2 times 0. And then we have 2 times 0 minus 1 times 2, which includes 0, 6, minus 2. And then for z, which is v cross u, we have 2, 0, 0, cross 2, 1, 3, which is equal to 0 times 3 minus 0 times 1, and we have 0 times 2 minus 2 times 3, and 2 times 1 minus 0 times 2. So we have 0 minus 2, 2, minus 6. So 0 minus 6, 2. This result makes one thing clear. Generally speaking, u cross v does not equal v cross u. Therefore, we say that the cross product is anti-commutative. In fact, it can be shown that u cross v is equal to minus v cross u. You can determine the vector returned by the cross product of the left-hand thumb rule. If you first aim your fingers in the direction of the first vector and curl your fingers towards the second vector, always taking the path with least angle, your thumb points in the direction of the returned vector, as shown in figure 111. To show that w is orthogonal to u and that w is orthogonal to v, we recall from section 3 that u dot v equals 0, then u is perpendicular or orthogonal to v, because u dot, in this case, w dot u is equal to the vector w, 0, 6, minus 2, dot the vector u, which is 2, 1, 3, and then that will be the product sums of the products of the corresponding components, which is 0 times 2, 6. The sum of the products of the corresponding vector product components. The dot product is the summation of the products of the corresponding components of the vectors. So we have 2 times 0 plus 6 times 1 times minus 2 times 3, in which case we have 0 plus 6 plus minus 6. The 6 plus minus 6 is 0. So the dot product of the dot products of w and u is 0, which tells us that our answer, w, is orthogonal to u, as it should be. And we could check the dot product of w and v to make double sure that it is both orthogonal to u and v. We have section 4.1, pseudo 2D cross product. The cross product allows us to find a vector orthogonal to two given 3D vectors. In 2D, we do not quite have the same situation, but given a 2D vector u is equal to u sub x and u sub y, it can be useful to find a vector v orthogonal to u. Figure 1.14 shows the geometric step for which it is suggested that v is equal to minus u sub y and u sub x. The formal proof is straightforward. U dot v is equal to the dot product of u and v, which is equal to u sub x times minus u sub y plus u sub y times u sub x, which is equal to 0. Thus, u is orthogonal or perpendicular to v. Observe that u dot minus v is equal to u sub x plus u sub y plus u sub y times minus u sub x, which is also 0. 2. So we also have that u is perpendicular to minus v. We have orthogonalization with the cross product. In section 3.1, we looked at a way to orthogonalize a set of vectors using the Gram-Schmidt process. For 3D, there is another strategy to orthogonalize a set of vectors v sub 0, v sub 1, v sub 2 that are almost orthogonal, but perhaps unorthonormal due to accumulated numerical precision errors. Using the cross product, refer to figure 1.15 for the geometry of this process. Looks like we have another glitch in the print or the scan. So we set something, then we set... I'm confused. Oh, the information is missing. Hold on, I have the book. What page is this? Page 60. Get us close. Okay. So here what's missing is we set w sub 0 to equal the unit vector of v sub 0. And then we set w sub 2 to equal the cross product of this w sub 0 and v sub 1. And then we finally set we set w sub 2, to be the cross product of w sub w sub 0 cross v sub 1 is w sub 2. And then we have the third step, which is we set w sub 1 to equal the cross product of w sub 0 and w sub 2. So, the cross of w sub 2 by w sub 0. By exercise 14, w sub 2 cross w sub 0 is 1 because both w sub 2 is perpendicular or orthogonal to w sub 0, and the length of w sub 2 is equal to the w sub 0. So we do not need to do any normalization in the last step. Okay. Notice, here's where we have a note. Notice that we did not change the direction of v sub 0. So w sub 0 is simply the normalization of v sub 0. And so we did not change the direction of v sub 0. However, the directions of w sub 1 and w sub 2 could be different from v sub 1 and v sub 2, respectively. Depending on the specific application, the vector you choose not to change the direction might be important. For example, later in this book, we represent the orientation of the camera with three orthonormal vectors: v sub 0, v sub 1, v sub 2, where the third vector, v sub 2, describes the direction the camera is looking. When orthogonalizing these vectors, we often do not want to change the direction we are looking. So we start the above algorithm with v sub 2 and modify v sub 0 and 1 to orthogonalize the vectors. Section 5 on points. So far we have been discussing vectors, which do not describe positions. However, we will also need to specify positions in our 3D programs. For example, the position of 3D geometry and the position of the 3D virtual camera relative to a coordinate system. We can use a vector in standard position to represent a 3D position in space. We call this a position vector. In this case, the location of the tip of the vector is the characteristic of interest, not the direction of magnitude. We use the terms position vector and point interchangeably, since the position vector is enough to identify a point. One side effect of using vectors to represent points, especially in code, is that we can do vector operations that do not make sense for points. For instance, geometrically, what should the sum of 2 points mean? On the other hand, some operations can be extended to points. For example, we define the difference of 2 points, q minus p, to be the vector from p to q. Also, we define a point p plus a vector v to be a point q obtained by displacing p by the vector v. Conveniently, because we are using vectors to represent points relative to a coordinate system, no extra work needs to be done for the point operations just discussed, as the vector algebra framework already takes care of them, seeing figure 1.17. With A being the difference between Q and P between 2 points is defined as the vector from P to Q. So we have final minus initial. And then we have part B of figure 1.17 with the point P plus the vector V is defined to be the point Q obtained by displacing P by the vector V. Note, actually, there is a geometric meaningful way to define a special sum of points, called an affine combination, which is like a weighted average of points. Section 6. DirectX Math Vectors. For Windows 8 and above, DirectX Math is a 3D math library for direct 3D application that is part of the Windows SDK. The library uses the SSE2, the Streaming SIMD Extensions 2 instruction set, with 128-bit wide SIMD single instruction multi-data registers. SIMD instructions can operate on 4 32-bit floats or ints with 1 instruction. This is very useful for vector calculations. For example, if you look at vector addition with u plus v, we see that we just add the corresponding components. By using SIMD, we can do 4D vector addition with 1 SIMD instruction instead of 4 scalar instructions. If we only required 3 coordinates for 3D work, we can still use SIMD, but we would just ignore the 4th coordinate. Likewise, for 2D, we would ignore the 3rd and 4th coordinates. I know that the SSE2 instruction set is included in an AMD64 Architecture, which is in another video I made prior. At least in overview, it was covered, or defined in it. If it's defined in the AMD64 Architecture Programming Manual, I imagine that it is supported by the AMD64 Architecture. Our coverage of the DirectX Math library is not comprehensive. We only cover the key parts needed for this book. For all the details, we recommend the online documentation for DirectX Math. For readers wishing to understand how an SIMD vector library might be developed optimally, and perhaps to gain some insight why the DirectX Math library made some of the design decisions that it made, we recommend the article Designing Fast Cross-Platform SIMD Vector Libraries by Oliveira in 2010. To use the DirectX Math library, you need to include DirectXMath.h header. And for some additional data types, we want to #include DirectX packed vector.h. There are no additional library files, as all the code is implemented inline in the header file. The DirectX math.h code lives in the DirectX namespace, and the DirectX pactvector.h code lives in the DirectX pactvector namespace. In addition, for the x86 platform, you should enable SSE2 in the project properties configuration properties C++ code generation enabled enhanced instruction set. And for all programs, you should enable the fast floating point model /fpfast. The project properties configuration properties C++ code generation floating point model. You do not need to enable SSE2 for the x64 platform because all x64 CPUs support SSE2. Okay, so let's check that. Just in this program. Here we are. So this is just the, okay. So we go to right click our project, properties, C++. What are we looking for? Code generation. Enable enhanced instruction set. Streaming SIMD extensions 2. Now we don't have to do this, but we can. And a floating point model, we can switch to fast and apply. Hit OK. Let's run this. Looks like we have to rebuild. And it ignored the architecture of the SSE2. And we have the same program as we had before. I am curious to note that the example program from the book doesn't follow what the book recommends. Hold on, I'm looking at the build. No, we want build. So we see here, warning D9002, ignoring unknown option. It's an unknown option. Interesting. So let's go back into here, properties, code generation, and let's just say not set. Apply. Okay. Save this and put this aside. Okay, we have section 6.1, vector types. In DirectX Math, the core vector type is XM vector, which maps to SIMD hardware registers. This is a 128-bit type that can process 4 32-bit floats with a single SIMD instruction. When SSE2 is available, it is defined like so for the x86 and x64 platforms. With type defined M128XM vector, where M128 is a special SIMD type. When doing calculations, vectors must be of this type to take advantage of SIMD. As already mentioned, we still use this type for 2D and 3D vectors to take advantage of SIMD, but we just zero out the unused components and ignore them. XM vector needs to be a 16-byte aligned. And this is done automatically for local and global variables. For class data members, it is recommended to use XMFloat2 for 2D, XMFloat3 for 3D, and XMFloat4 instead. These structures are defined below, with the struct XMFloat2 to be a float x and a float y, a simple constructor, and a simple constructor with parameters taking in float of x and y, and explicitly reading a constant float array pointer of size 2 with inreads macro. With the pointer to the array, we want to set our x and y to be the first and then second component of the array. And then finally, we have an operator overload where the XMFloat2 address operator is equal to the constant XMFloat address float2 x is equal to float2.x. So I'm not quite sure. Are we passing a constant address of itself? Yes. That's odd. Bit advanced C++ right there. I'm not quite sure exactly what's happening there. I'm not even sure if it's C++. But effectively, the address operator... Is it the address operator? Strange. It looks to be that if we're trying to grab the address of an XMFloat2 value, we create a constant and then return a pointer to that constant. Interesting. Then we have the struct XMFloat3, which is defined with 3 floats, x, y, z, XMFloat, and it has similar constructors: an empty constructor, a constructor with 3 parameters of floats, and then we have an explicit float, which reads from an array, if given an array. And then we have another operator overload similar to above, and XMFloat is similarly exactly the same as above, simply with one more additional member, W, X, Y, Z, W. However, if we use these types directly for calculations, we will not take advantage of SIMD. In order to use SIMD, we need to convert instances of these types into the XM vector type. This is done with the DirectX math loading functions. Conversely, DirectX math provides storage functions which are used to convert data from the XM vector into the XMFloatN types. To summarize, use XM vector for local or global variables. Use XMFloat2 and XMFloat3 and XMFloat4 for class data members. Use loading functions to convert from XMFloatN to XM vectors before doing calculations. Do calculations with XM vector instances and use storage functions to convert from XM vector to XMFloatNs. Section 6.2. Loading and storage methods. We use the following methods to load data from XMFloat into XM vector. will be load an xmfloat2 into xmvector using the call convention xmloadfloat2, which takes in a constant xmfloat2 pointer source, a pointer to a constant xmfloat2 source. And then we have the xmloadfloat3 function, which takes a const pointer to an xmfloat3, or a pointer to a constant xmfloat3 source. Similarly, we have one for loadfloat4. We use the following methods to store data from the xm vector into the xmfloatn, in which case we do xm store float2, and we use an xmfloat2 pointer destination, and from a fxm vector v. And similarly, we have one for xmfloat3s and xmfloat4s. Sometimes we just want to get or set one component of an xm vector. The following getter and setter functions facilitate this with the call convention xm vector get x, xm vector get y, xm vector get z, and xm vector get w, with the following setters with the xm vector set y, x, y, z, and w respectively. And we have 1.6.3, or section 6.3 of chapter 1, parameter passing. For efficiency purposes, xm vector values can be passed as arguments to functions in the SSE and the SSE2 registers instead of on the stack. The number of arguments that can be passed this way depends on the platform. For example, 32-bit Windows, 64-bit Windows, and Windows RT and compiler. Therefore, to be platform or compiler independent, we use the types fxm vector, gxm vector, hxm vector, and cxm vector for passing xm vector parameters. These are defined to the right type based on the platform and compiler. Furthermore, the calling convention annotation xm underscore callconv must be specified before the function name so that the proper calling convention is used, which again depends on the compiler version. Now, the rules for passing xm vector parameters are as follows. 1. The first 3 xm vector parameters should be of type fxm vector. The fourth xm vector should be of type gxm vector. The fourth and fifth xm vector parameter should be of type hxm vector. Any additional xm vector parameters should be of type cxm vector. We illustrate how to use these types are defined on 32-bit Windows with a compiler that supports the fast call calling convention and a compiler that supports the newer vector call calling convention. 32-bit Windows fast call passes free xm vector arguments via registers, the remaining on the stack. Okay? The 32-bit Windows vector call passes first 6 xm vector arguments via registers, the remaining on the stack. For the details how these types are defined for other platforms, see calling conventions, other library internals, and the DirectX math documentation. The exception to these rules is with the constructor methods. Recommends using fxm vector for the first 3 xm vector parameters and cxm vector for the rest while writing a constructor that takes xm vector parameters. Furthermore, do not use the annotation xm_call convention for constructors. Here is an example from the DirectX math library. We have an inline function that returns an XM matrix using the xm_call convention, which the function name is called XM matrix transformation, which takes into parameters fxm vector, xmv vector, fxm vector, a gxm vector, and an hxm vector and hxm vector. This function takes 6 xm vector parameters, but following the parameter passing rules, it uses fxm vector for the first 3 vectors, or first 3 parameters, gxm vector for the 4th, and hxm vector for the 5th and 6th. You can have non-xm vector parameters between xm vector parameters. The same rules apply, and the xm vector parameters are counted as if the non-xm vector parameters were not there. For example, in the following function, the first 3 xm vector parameters are of type fxm vector, and the 4th xm vector parameter is of type gx vector. Okay, interesting. So we have the inline function that returns an XM matrix using the XM call convention, which is the XM matrix transformation 2D function, which we have an fxm vector for scaling origin, a float for scaling orientation, an fxm vector for scaling, an fxm vector for rotation origin, a float for rotation, and finally a gxm vector for translation. So the first 3 are of fxm vectors, and then finishing off with a gxm vector for translation. The rules for passing xm vector parameters apply to input parameters. Output xm vector parameters, xm vector addresses, or xm vector pointers, or ASCIIs, will not use the SSE or SSE2 registers, and so will be treated like non-xm vector parameters. It was getting a little complicated quite there for the calling conventions using the SSMID architecture. And so looks like my learning into the AMD64 architecture is not unwarranted. If I understood that architecture a little bit more and its calling conventions and whatnot, I think I could understand what the book is talking about right now. I'm about 80% lost about why, what's going on and why, but I do understand that it's packing the data in an efficient ordering, as such that it can bring over multiple pieces of data all at once and use multiple pieces of data all at once. And I'm confused about the GXM and HXM vectors. Confused about them myself. I don't understand why they are different. Section 6.4. Constant vectors. Constant XM vector instances should be used with the XM vector F32 type. Here are some examples from the DirectX SDK's Cascade Shadowed Maps 11 sample. We have static const XM vector F32 variable called G_V half vector, which is equal to a half float, so 0.5 float for its X, Y, Z, and W components. And then we have also another constant XM vector 32 for V sub 0, which is defined with zeros for all components of the vector. We have an XM32 variable being set to be with its x component being the right slope of the view frustum, the y component being the top slope of the view frustum, and then 1 and 1 for our z and w components. And we have that copied below. We'll have that below as well for an XM vector F32, which is left bottom, which is the x and y being of left slope and bottom slope of the view frustum, and a 1 for z and w. Essentially, we use the XM vector F32 whenever we want to use initialization syntax. XM vector F32 is a 16-byte aligned structure with the XM vector conversion operator. It is defined as follows. So the struct XM vector F32 is 16-bit aligned using some compiler flag right there, or calling convention. Not quite sure where macro, kind of hard to describe. Where the underscore decal spec. And we have a union. A union. Is a union a C type structure? Or is a union a struct? Union. Just checking my C programming book. Union initialization and union specifier are the union tag to page 212. Okay. A8.3 Structures and Union Declarations. A structure is an object consisting of a sequence of named members of various types. A union is an object that contains, at different times, any one of several members of various types. Interesting. Structures and union specifiers have the same form, so they look identical. That's what tipped me off. That it was a C structure, or a C thing. A union is an object that contains at different times any one of several members of various types. Okay. So any one of several members of various types. Okay, so it's a union. The XM vector F32 can be two things with that union. It can either be an array of size 4 of floats, or a single XM vector V. Okay, so we just learned a little bit right there. Learned a little bit about C as well. That's an interesting component. Do. Can be both? Confused. Because this operator here of this struct, so this struct XM vector F32 has the operator override of parentheses to return a constant operator which returns the value v, the xm vector v union. Okay. We have the inline operator const float star. Star parentheses, constant, return f. Okay, so we're doing operator overloading here. Now, I don't know what this operator is, though. This star, float star. No, that's not it. It's just the asterisk? It returns a float pointer, and it uses the parentheses. I think it's the parentheses as the operator that's being overloaded. And we have some quite complex things where we have a definition check using the SSE intrinsics. No intrinsics. I'm not quite sure about that. So I don't know what those flags are, or what those definitions are, and where they come into play. No intrinsics and SSE intrinsics. I don't know what intrinsics is. And then we have some more macros, or calling conventions, below. Operator overloading the parentheses. Either returning an I128-bit vector v, the xm vector v, or we'll be casting the v. I'm not quite sure what's going on here. I'm very confused. Very confused. Let's just continue on, and hopefully as we learn the AMD64 architecture a little bit more, this can come back at to us, as well as reread and reread and reread and reread the C programming language itself. So to understand what is going on down here, this is mostly C code. We're very low-level programming. You can also create a constant XM vector of integer data type using the XM vector U32. Section 6.5, Overloaded Operators. The XM vector has several overloaded operators for doing vector addition, subtraction, and scalar multiplication. So we have addition, subtraction, positive, what would you call that? Positive equal to, but that's more of like a plus equals, minus equals, times equals, divide by equals, times equals, divide by equals, a scalar equals scalar division by a float. And then we have two FXM vector additions. We can add two FXM vectors to get an XM vector. Plus, minus, times, divide. And then we can do a scalar multiplication. A scalar multiplication with the float first or the float after. Interesting. Well, it gives us the option. And then we have, I wonder if there's any difference in that code. And then we have the division operator between a vector and a float. Yeah, chapter 1, section 6.6 on miscellaneous. The DirectX math library defined the following constants useful for approximating different expressions involving pi. We have xm pi, xm2 pi, xm1 divided by pi, xm1 divided by 2 pi, and xm pi divided by 2, and xm pi divided by 4. In addition, it defines the following inline functions for converting between radians and degrees. We have inline float. We have inline function returning a float called xm convert to radians, which takes in a float f degrees argument and returns the f degrees times xm pi divided by 180 degrees. By 180 degree float. And then we have the xm convert to degrees function, which returns a float, and we get in a float of radians, and we return the radians input parameter times the multiple of 180 degrees divided by xm pi. It also defines min-max functions. So we have xm min, which takes in a class type t. So a template, this is templated, and we okay, this is not very useful, but I mean it is useful, but it isn't. I don't even know what's possible. Okay, it simply has the lambda function a less than b question mark a colon b. So if a is less than b, it returns a. If it's not that, it will return b. And then we have max, which checks for a is greater than b. If it's true, it returns a, and if it's false, it returns b. I think that's a lambda function. Am I right about that? Time to go back to the book. Lambda functions. Lambda. No, it doesn't look like a lambda function. Trying to find it. I'm not seeing it yet. I think it ought to be in here. Somewhere. Here we are. Macro substitution. So it has it as macros. Interesting. Hold on. Macro substitutions. The simplest kind. Subsequent occurrences of the token name will be replaced by the replacement text. And so we can have it define max a comma b. It checks for if a is greater than b, then it's a question mark, and it either has a or b. Although it looks like a function call, the use of the max extends into an inline code. Okay. Each occurrence of the formal parameter, here a or b, will be replaced by the corresponding actual argument. So long as the parameters are treated consistently, this macro will serve for any data type. Any. There is no need for different types of max for different data types, as there would be with functions. Okay. So it is C. preprocessor. The question mark operator, the question mark token. I'm looking for it, more defined. Oh, we register. Oh, yeah, that's old stuff. I'm not seeing it. You sort of get the picture, though. If the statement before the question mark is true, you get the left hand colon. If it's false, you get the right hand colon. Chapter 6, Chapter 1.6.7 Setter Functions. DirectX Math provides the following functions to set the constants of an XM vector. We have XM vector 0, which returns the 0 vector. We have XM vector splat 1, which returns a vector of 1, 1, 1, 1, 1. We have the XM returns the vector x, y, z, w, which is XM vector set with a float x, y, z, w. And we have return the vector SSSS, which XM vector replicate float value. And we have return the vector v sub x, v sub x, v sub x, v sub x. So we take in, so XM vector splat x, you take in, it returns an XM vector, it takes in an FFXM vector v, and it just copies that x value across the XM vector it returns. It does that similarly for splat y and splat z. The following program illustrates most of these functions. We include the windows.h header. We include the DirectX.h inline header, as well as the DirectX packed vector.h inline header, and we include the IO stream from the standard library. We use the namespace as std. We use the namespace DirectX, and we also use the namespace DirectX packed vector. We have a comment here that overloading the double left-handed bracket, or I think the input operators, so that we can use cout to output XM vector objects. So it looks like we override it here with the output stream and calling convention flag or macro operator, input operator, OS stream, and OS FXM vector v. So we're defining this function that overrides the double left hand or the input operator. We take in an XM float. Well, we create an XM float free destination. We store that information from the XM vector v to that destination, and then we print out to the output stream a formatted information, so a left-hand parenthesis, the x variable separated by a comma and space, the y variable separated by a comma and space, the z variable capping with a parenthesis, and then we return the object stream or the output stream. And then we have the function int main, so the main function. We have cout, set if, iOS base to Boolean alpha. I'm not sure what that is. Check if support for SSE2, Pentium 4, AMD K8, and above. Ooh! Oh, that's interesting. Hold on. I got my CPUs in my pocket. I have an Intel Pentium in my hand. Hold on, I need a flashlight. I don't know why they decided to print gray on black. Bad choice. Intel Pentium, this is a 8150 or 5P100. I don't know if it's a Pentium 4 at all. kind of hard to tell. But I do have an AMD K6. Ah, bummer. So 1998. When this one was made, the AMD CPU I have in my hand was 1998, and this one is from 92, 93. Old CPUs. So they don't support that. Here we go. But we can check the CPU support. That's interesting. XM verifies CPU support. We have the if. That's cool that there's a function available to us that we can put in our code that will tell us if it's true or not that the CPU that we're using supports SSE2. Now, considering that we have an AMD Ryzen X 1800X well above the AMD K8 and the Pentium 4, which is well above the AMD K8. I'm sure we support it. And actually, wait a minute, I don't even have to care about that. Forget about that. I've been reading the AMD64 architecture. The AMD64 architecture is clearly defining the SSE2 in its definitions in the beginning of the book, the preface. So it must support it. I think it supports well more than that. So we know it's supported. We don't even have to check it for my computer specifically. My computer. It could be for other computers, it may not be, but pretty much I think any computer running today that wasn't purchased and sat in the living room for eternity or taken out of storage will rephrase it. Any computer purchased within a few years is probably going to support that SSE2 optimizational architecture of the SSIMD extended to. Is it SSE2? Hold on. Extensions to the SSE instruction set with SSS extreming SIMD extensions, which is instructions to operate on scalar or vector packed integer and floating point numbers. The SSE instruction set comprises the legacy SSE and extended SSE instruction sets. So we have it defined here. That doesn't mean it supports it, but I'm pretty darn sure it's going to support it. AMD features, okay. Registers, maybe it has it in here. We have registers, instruction set. Okay, here we are, right here. AMD64 Architecture supports the full legacy x86 instruction set with additional instructions to support long mode. The application programming instructions are organized into 4 subsets as follows. So we have the general purpose one, but then we want to look at the second one. The streaming SIMD extensions instructions. These instructions load, store, and operate on data located primarily in the YMM and XMM registers. 128-bit media instructions operate on the lower half of the YMM registers. SSE instructions perform integer and floating point operations on vector packed vectors and scalar data types. Because the vector instructions can independently and simultaneously perform a single operation on multiple sets of data, they are called single instruction multi-data instructions. They're useful for high-performance media and scientific applications that operate on blocks of data. Now, it doesn't say that it does SSE2. search for SSE2. Okay, here we go. The SSE instruction set includes instructions originally introduced as extensions, herefore referred to as SSE1. The instructions added to the subsequent extensions. Okay, so many. Collectively, the SSE1, 2, 3, SSE 3, SSE 4.1, 4.2, and SSE4A subsets are referred to as the legacy SSE instructions. All legacy SSE instructions support 128-bit vector operands. The extended SSE instructions include... Okay, so this is defining it. All extended SSE instructions provide support for this. Okay. Ow. Okay, still, I'm not finding it. Okay. System software implications supporting applications that use the streaming SIMD extensions. Throughout this chapter, instructions collectively... Okay. Again, it keeps defining what the SSE is, but not if the AMD64 follows it or has it. I think it just goes without saying. It literally has gone without being explicitly said. System software must determine if SSE subsets are supported, enabling those that are to be used, and supply the code handle the various exceptions that may occur. Unique exception handling. Enabling extended SSE execution. Interesting. So we could check it with this command down here. We can check if it supports these instructions. Down here. Okay, so the AMD64 architecture is not explicitly saying that it supports it, but it is providing ways of checking if the CPU that we're running these commands on has that functionality. And so we can do that with these instructions below. And so if the hardware supports x87 legacy SSE and extended SSE instructions, bit 0 of the EAX register signifies the x86 floating point and MMX support, and bit 1 signifies that there's legacy SSE support, and bit 2 signifies extended SSE support. Support for both x87 and legacy SSE instructions are required for processors that support extended SSE instructions. Interesting. Okay. Still is not explicitly mentioned, but that's okay. We can take assumptions when we can. And so we have figure 1.18 or 1.18 output for the above program. Okay, so I'm going to stop it here so I can give my voice a break, give me some time to move around, get some exercise, and then we'll come back to this, and I will bring in this program that we see written in the book here, and I will copy that program and make a make a program of this, and we'll go over the program to see if it worked, it didn't work, and checking the CPU support and whatnot. It'll be interesting to see if the XM Verify CPU support is using any of those functions talked about in the AMD64 architecture programming manual. Okay, so we'll see that in the next video. Thank you for watching. Hope you found this helpful as we slowly eat our way through this complicated topic.